Hello and welcome to my AC circuits um, presentation. We are going to be continuing on with what we learned on Monday in this presentation. So just a quick review. Last class we discussed equations for voltage across an inductor, capacitor, and resistor. These are equations that are time-based, and we learned that the voltage at any given time across an inductor leads the voltage across the resistor by 90 degrees, and the voltage across the capacitor lags behind the voltage across the resistor at any given time. And another important note is that the voltage across the resistor is in phase with the current flowing through it, which is the current that the source is outputting. So now we'd like to define something called reactance. So basically a reactance is how does a capacitor or an inductor affect current flowing through it. Obviously that in an AC circuit, when current flows through a capacitor or through an inductor, there will be some effect on that current, whether it be to slow it down or to speed it up or things like that. So that's what reactance is discussing and allowing us to analyze. So these values of reactance are measured in ohms, and if we were to take a look at the units here, you can verify just by looking at the units that they give units of ohms. And as also shown, these vary with frequency. So an increase in frequency results in an increase in X sub L and a decrease in X sub C, as I kind of talked about last class. So on this slide, what I'm showing is that using reactance, we can kind of look at the voltage equations for the capacitor and the inductor as Ohm's law type equations. So it's like a V is equal to I times R, where R would be our reactance. So what we're really getting at is trying to analyze AC circuits in a similar way to DC circuits, as you can see here. So continuing on with that thought, we're going to define impedances. So impedances are any restriction to current flow in an AC circuit. So energy is lost from the current flow, whether it be stored in the electric or magnetic fields of the capacitor and inductor, or whether it be lost in the form of heat across a resistor. So we've got three different impedances. We've got resistive impedance, in which case we're just using variable R or the actual value of the resistor, say 10,000 ohms, 5,000 ohms, whatever it may be. We've got inductive impedance, which is X sub L, or reactance X sub L, which would be the inductive impedance. And we have capacitive impedance, X sub C. So in order to calculate total impedance in a circuit, we're going to need to find a way to add these three impedances together. And that's what I'm going to talk about in the rest of this presentation. Okay, so what we're going to consider for the remainder is something called an RLC series circuit, as shown. So we've got a resistor, an inductor, and a capacitor all in series attached to an AC source, as shown. So this actually has values in it for you to be able to do calculations if you're interested in going through examples, plotting something in Excel and seeing how these curves look, things like that. And I highly recommend practicing with this. So the first thing we're going to do here is note that we can apply Kirchhoff's voltage rule at any instant in time. So it's important to note that at any instant, the source voltage has to be equal to the sum of the element voltages. And the reason is that we're gaining potential across the source, but then losing potential across each of the three elements. So summing them together shows that the three element voltages have to equal the source voltage. And so now we're going to take a look at what those voltages are. based on the last equations that we derived. And we have to find a way to add these. Now, one thing to notice is that they're out of phase with each other. So, if we added them up just as scalar quantities, we're going to end up with a very complex equation dealing with cosine omega t, and then cosine omega t plus pi over 2, cosine omega t minus pi over 2. How do you add them together? There's no clear way of adding them together. So what we're going to end up doing is using something called a phasor diagram. And this diagram is just a way of looking at this circuit, a way of looking at the equation so that we can properly add the reactance and the resistance in order to get an equation that makes sense. So again, a phasor diagram is a way of looking at this circuit, and essentially all it is a vector diagram showing current and each voltage as a rotating function of time. So here is the basic idea behind a phasor. So as the line rotates, this basically sweeps out the current oscillating in time. And any line that we put on this graph and rotate will also give us a sine curve type function like this, as you can imagine. And on the right-hand side, what we're showing is that this rotates with cosine omega t, angular speed omega, 2 pi f. And so if we were to project this current I, which is the amplitude of this of the current, onto the x-axis or horizontal axis, we're going to get I cosine omega t, which is real-time current. So now what we're going to do is we're going to add in the 3 voltages in question. So we're adding in voltage across the resistor, which is nothing more than a vector that is in phase with the current as shown on the right-hand side in red. And then voltage across the inductor, which has to be 90 degrees out of phase. So that's why the V sub L term is at a 90-degree angle to the current as shown, pointing off to the top left there. And then voltage across the capacitor has to be negative 90. So that's why that the voltage across the capacitor is shown down and to the right. Both of these are in green as shown. So hopefully this is making sense, where we've got currents rotating around the origin. Voltage across the resistor would rotate with it and stay in phase the whole time. Voltage across the inductor and the capacitor would be 90 degrees plus and minus, and they would also continue to rotate so that they're constantly staying at 90 degrees to the current. So what you're looking at here are amplitudes, capital V sub L, capital V sub C, capital V sub R. And when we project them using cosine, we're going to get the actual magnitude in real time. So that's kind of the idea behind this phasor diagram. So we add these voltages now, as we can see, as a vector sum, and the vector sum of these voltages has to equal the source voltage based on Kirchhoff's rule for voltages. So first of all, we're going to take only the inductance and the capacitance. So we're going to look at V sub L and V sub C and add those 2 vectors together first. So starting with the inductor and capacitor, since they're on the same line as each other at all times, it's very easy to add them. It's a matter of just vector subtraction. So adding these 2 vectors that are exactly 180 degrees apart results in VL minus VC, which is the vector here shown in purple. And on the bottom of this slide, notice I say that uppercase denotes amplitude. So we're dealing with only amplitudes here so far. So VL and C basically is the sum, which is VL minus VC. And as shown, that has to equal IX sub L minus IX sub C, using the Ohm's law equation. Okay, now we're going to place that vector back onto our original phasor diagram. noting that it's exactly 90 degrees apart from V sub r. And so adding these two vectors together is also straightforward. We can use Pythagorean theorem, or imagine that these are two vectors, one along, say, the y-axis and one along the x-axis. So in order to add them, we're using the square root of the squares. And so this is showing just that. So we're adding the vectors up using a parallelogram type vector addition or square root of the squares, Pythagorean theorem. And so that gives that V source has to equal V sub r squared plus V ln c squared by simple vector addition. And so now what we're doing is we're plugging in each of these voltage values in terms of current and resistance and reactance. So now we have an equation in terms of nothing but impedances and current. And so we can see here we can factor current out of each of these terms under the radical. My apologies for the one vector rotating, so that's an animation that's not supposed to be in here. But as we can see, we factored out the I squared term, and now we're left with an equation in terms of I squared separated from our impedances. And further separating this equation, we have some equation that looks like V is equal to I times R again, sort of like an Ohm's law type equation. And so now we're going to find something called total impedance, which is Z. Okay, so total circuit impedance is equal to resistance squared plus XL minus XC squared. And then that allows us to write sort of the V is equal to IR relationship that we're looking for here. And I'm showing V sub source on the phasor graph, and I'm showing the original current, and you can note that V source is out of phase now, or leading the current in this particular example. And so here's the equation, V source is equal to IZ. Now I also wanted to find something called phase angle. So this phase angle is angle between source voltage and source current. And we can bring back our original vectors here in order to determine how do we calculate phase angle. Okay, so phase angle is calculated. Tangent phase angle is opposite over adjacent, which is shown here as VL minus VC, that's the opposite vector, divided by V sub R, which is the adjacent vector. And now we're gonna bring back what each of the voltages are, which are in terms of reactance and resistance, in order to further define tangent of phase angle as the difference between reactance divided by the resistance of the resistor. And now bringing back what these reactants actually are as far as in terms of frequency, we can see that phase angle is affected by the frequency of our source and by whatever our capacitor and our inductor values are. So we can definitely tweak phase angle and change it to what we want depending on how we set our power supply. So that's very important. And for the final step of the presentation, what I want to show now is that the current of the source and the voltage of the source have the relationship that they are out of phase by the phase angle. So essentially now we know how to calculate each of these, whereas current of the source is just simply magnitude of the current or amplitude of the current cosine omega t, and voltage of the source is V source, which is I times Z, which is impedance, right? Times cosine omega t plus the phase angle. So if we wanted to reduce phase angle to 0, the way that we're going to do this is by making the numerator of the tangent theta equation equal to 0. And the way you do that is by setting the reactance due to the inductor equal to the reactance due to the capacitor. And that's called tuning the circuit. So we're going to talk about that next class, how to tune an AC circuit and get maximum current amplitude out of it. So thank you for watching, and please be sure to email me with any questions you have, and practice going over some of the examples that are listed on the online worksheet.